the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal to mc squared, in which energy is press equal to mass multiplied with the square of the velocity of light, shows that very small amount of mass will be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cochran experiment.
Einstein. Hello. So I just like hearing him say vice versa.
When did he die?
55, I'm guessing. I don't have it memorized. I'm not a historian.
Wait, what year?
1955. Yeah. Oh, how old is he there? He's 70-something. He lived a good life. German, relocated to America. Do you think he cared what his hair looked like?
Yeah.
No. Now there is, hang on. So there's a story, not really ask him, but lots of stuff's been written down. He didn't care what his hair looked like. He could care less about what he wore in the day. He was thinking about more important things. So the last thing he wanted to do when he got up in the morning is look in his wardrobe and go, what do I put on? Do I put on the blue suit? What people might think if I put on the blue suit. Maybe it has to do with the weather today. Maybe I'm giving the wrong impression. Maybe I'll put on the green suit. No, that would imply maybe that I'm in a good mood. Maybe I should put on the red suit. So what he did was just buy 7 suits, 1 for each day of the week. That's my Monday suit. That's my Tuesday suit. So on and so on. Every one identical, brown. In style, in color, in size. He didn't have to worry about what he was going to put on each day.
Was that it?
What? My story?
No, what he's wearing then.
Was that the suit? I don't know. Okay. Again, I've never asked him. I wasn't alive, when I could have. But that's the story, right? This is one of the best minds that have ever walked the planet. So let's save that energy for things that actually matter and not worry about what I'm going to wear each day. So these look like some pretty heavy-duty equations. It's a kind of mathy stuff. We're not doing it today. Before we can talk about him or what's special, we need to first get on grips on what this word relativity means. Remember the first thing I gave you in this course? It's a little kind of a fill-in sheet. And it said, is a loaf of bread hard? And I got all sorts of different answers because you all come from different experiences. And what are you comparing that thing to be? Compared to a block of stone, bread's kind of soft. Compared to a bowl of Jell-O, bread can be kind of hard. Okay, so it's like a relative question. Are you moving right now?
Yes.
You are.
I think so.
And because I've maybe said it before, or maybe you're at experience that you know the real answer, but you can understand that most people, if I ask them when they're sitting in a chair, if they're moving, they say no, right? But why do we say we're moving, Jeff? You just think that psychology, well, the answer should be no, so I'm just going to say yes? Okay. Calvin, are we moving? Why?
Yeah.
Okay, so the Earth, yes, is rotating around the sun. How fast? 100,000 miles an hour. No, approximately. And what else is the Earth doing? Spinning. Does it really? Because I was talking to someone earlier about looking up some YouTube videos that there's a conspiracy. NASA's feeding us a load of, it doesn't spin. Remind me later, I'll show you the video. It's kind of funny. Anyway, yes it is. I'm telling you it is. How fast is this thing rotating? So this is actually called revolving. This is called rotation, spinning. Same thing, right? That's 1,000 miles per hour. This is 100,000 miles per hour. So you're not only moving, you're moving in two different directions. But wait a minute, what season is this? Have we tilted away from the sun so the rays aren't as direct? So even when the sun shines, it doesn't feel as warm as the summertime? So you're actually tilting as well. Now the speed of that isn't that much, but you're actually moving right now in three different directions. Okay? So again, it's a relative question. That's all I'm trying to say. What's this? A ball. If I throw this straight up, according to me, that ball went straight up and then straight down. What did it do according to you, Colton? Straight up and straight down. But if I start moving with this ball, you tell me now what it's doing. It is going to your left if I walk to my right. But according to me, if I go to your right, it's moving. If I go to my left, it's moving to your right. Okay. According to me, it's still going straight up and down, isn't it? Yeah. Okay? So if this is going straight up and down according to me, but according to you, the faster I go, the more it's going to move, right? Well, then who's right? Is this ball going straight up and down, or is it moving left or right? It depends. Who's right, though? We both are. That's one of the first postulates that Einstein came up with in this theory of relativity. It's equally correct in everybody's frame of reference. Okay, so it seems like common sense, but we're going to take common sense to the next level. Okay, so a little bit of history. Feel free to read it. And the handout I gave you, some of these dates aren't exactly lining up. I don't know which one's right. I don't know which one isn't. Okay, I'm not here to teach history. I'm here to teach some physics. Page 261. There's some things going on here. One, let's look at, there's a guy in a boat. And this says the boat is moving at 10 kilometers per hour, but it's not just 10 kilometers an hour. We need to now think in terms of what? Relative to what? Well, it tells us relative to the water. That should maybe make sense. How about the man? What's the velocity of the man relative to the water? Is it still 10 or is it something different? Yeah, we're assuming the guy doesn't move in the boat. So if he's fixed in this boat and the boat moves 10 relative to the water left, then he also moves at 10 to the left. Okay? But now, if I want to know what's the velocity of the man relative to Earth, this doesn't give me that information, does it? Because that has nothing, the word Earth isn't in there. So I need something else. What's this say? The river velocity relative to Earth is 5, which means, in common sense terms, the speed of the water is 5 kilometers an hour to the left. So is that going to make this man, relative to someone sitting on shore, faster than 10 or slower than 10? Faster. Because if he's in here going 10 to the left, but the water is also going 5 to the left, then according to someone on Earth, on the shore, he's moving at 10 plus 5, 15 to the left, right? Everybody okay with that? Okay, so 15 is what he's doing. Let's look at the birdies. What is the velocity of the bird? And I can't just ask that question, can I? Because compared to what? You ever seen birds just sit there? As far as you're concerned, they don't even move. So they could be flying at 10 meters a second, let's go 10 kilometers an hour, but if the wind is going the opposite direction as the bird at 10 kilometers an hour, according to you, is he moving? No, he's just sitting still. So this bird, first of all, the wind is 20 to the right, relative to Earth. The bird is 25 relative to, now let's do ourselves a favor and cross out air and put wind, because that's the same thing. So if this bird flew at 20 relative to the air and the wind blew at 20, as far as you're concerned, standing on Earth and not moving, is he moving? No. But it's not 20. He's doing 25. So according to you, what's the net result of 20 right and 25 left? Yeah. Relative to Earth, that bird seems to be moving at 5, and I'm not going to put direction here. Left. So far, so good?
Yeah.
Okay. What is the velocity of the man relative to the bird? Well, this is a bird. Okay, it tells you what it does relative to the wind. I know what the man does, because that's the same as the boat. That's relative to the water. Can I compare those two?
Yeah.
No. Okay? Because that's like saying, you know, I'm going in a spaceship the same speed as Saturn, and then you're going in a spaceship the same speed as Earth. Therefore, our speeds must be the same, right? Doesn't make any sense, because you know the two planets are moving at different speeds. Okay, I can't compare this. I have to have something common, some common comparison. So I could do the bird relative to the water, and then the man relative to the water, and compare it. Okay, but I could also do each compared to Earth. Do I have those? Yeah. The man relative to Earth is 15, and the bird relative to Earth is 5. Okay, so what is the man relative to the bird? So the man is going 15, right? Okay, and the bird relative to Earth, if this pen will work, is 5. This is the same frame of reference. So now I can compare them. What's the difference there? The man relative to the bird is 10. Okay? If he's going 15 and the bird's going 5, then according to the bird, he's moving 10 to the left. Well, I don't know if I should say this, but I will. So if I had this reworded the other way around, and if it was the bird to the man, it would just be 10, but in the other direction. If I took this way as positive, then it would be negative 10. Okay, but don't worry about it. We got enough maybe on our heads right now. Okay, so kind of confusing, but relativity, I'm going to give you those to do. Now let's look in my little handout. Frames of reference. Again, a little more history of Einstein. And one thing I'll point out. So everyone was okay with Newton and his force of gravity, and we still teach it that way, right? Gravity is a force. It sucks this ball down towards the center of mass. And then he comes along and goes, well, you know what? It's actually a curved field in space and time in the presence of mass. And everybody on the planet at the time goes, what is he talking about? This guy's a lunatic. And some 13 years later, you know what? Yeah, we had an eclipse, and we noticed that this light from this star actually did look like it came from somewhere else. So he was correct in predicting that light will bend under the presence of a really strong mass. Maybe he does kind of know what he's talking about. Let's check out his other theories. Yes, a clock does move slower if it travels at a really fast speed. And then, of course, then he was taken as a genius. Now, he didn't actually get his Nobel Prize in this. He got it for the photoelectric effect, something else. Okay? Anyway, let's look at this. You guys know who this is? He actually, there's a movie out on him right now.
I want to see it.
Yeah, it's supposed to be pretty good. They announced actually just this morning the Academy Awards, and it's up for best this and best that and everything else. Best actor too. He kind of looks like him too. It's kind of good. Anyway, this is from him. Frames of reference. Two people riding in a train from New York to San Francisco. That's the US in a half a second. New York, of course, you guys know, is on the east. San Francisco is on the west, right? They're playing a game of ping pong. Okay? Yeah, on the train. Okay? There's a sports section in the train. They have a ping pong table. They're playing ping pong. Just go with it. All right. Okay, the train moves at 100 kilometers an hour from New York to San Francisco. Let's use physics units, 27.8 meters a second. Okay? The two players hit the ball. The ball between paddle and paddle is 2 meters a second. Okay? In the frame of the players, what happens? What would you see if you're playing? You would see the ball go away from you, 2 meters a second. Then he hits it back, and it comes to you at 2 meters a second. Or from a person standing beside you, let's say these guys, if that's the train car, let's say these guys are playing, okay? There's one guy, there's the other guy, and there's my ping pong, ba-dunk, ba-dunk. You're standing on the side of the tracks watching these guys through this glass playing ping pong, right? So first, according to them, what's the motion of the ping pong ball? It just goes like this, right? And then it goes back. But if you're standing outside and this thing's moving at 100 miles an hour, what would you see this ping pong ball do? It would go, and again, I drew it this way, so it would go like that. If you hit it that way, and then if you hit it back, it would go like that. And then if you hit it that way again, it would go like that. And then if you hit it back, it would go like that. So according to you, because the ping pong ball's only going 2, but the train's going 27.8, it's always going in the same direction, isn't it? Open your mind. No, it would not. Because in one direction it's going, it says it here, 29.8, and when it goes backwards, it goes 27.8 minus 2, 25.8. Well, that's still the same direction, right? If you're far away, it's not good. You're not standing right there. If you're far enough away, you're going to watch the ping pong ball do that. Okay? So who's right? They both are. They're just in different frames of reference, just like me throwing the ball. Okay? Now, one step further. There's a guy out in outer space, and he's watching this ping pong ball through the glass roof on this train. But what he sees is, because of the way the Earth spins, if you believe that the Earth spins, even though this train's going that way, all he sees is the ping pong ball going in that direction. Because 1,000 miles an hour, or the spin, is a lot quicker than 100 kilometers an hour, right? So it doesn't matter that the train's moving. The sun rises in the east and it sets in the west. So this is spinning in this direction. So even if you're traveling at 100, it's going that way at 1,000. Okay, so now we got 3 different frames of reference. Y'all confused yet?
Now somebody on the sun, and they're watching the Earth spin.
Yes, and so on, and he tells 2 friends, and he tells 2 friends, and yeah. Okay? Cool stuff. So all of the above is correct. It depends on your, what are we talking about? Fill in the blank. Frame of reference. So, which brings us to the first postulate of relativity. Are you supposed to know this for the test? If you want the mark, you need to. Einstein's first postulate of relativity. The laws of physics are the same in all inertial, and the next part is kind of, I just don't want you to look back at this when you have doctorate degrees in physics and go, hey, he made a mistake. So I will put non-accelerating, but it doesn't really matter whether you have that part or not. Reference frames. Okay? Which means, just because I'm throwing this ball up or down, the laws of physics, kinematics in particular, apply to me, but they also apply to you watching this ball. So we're both right. And you can argue, well, it doesn't really move sideways if I'm the guy throwing it, but according to you, it does. We're both correct. In all frames of reference, can you read that okay? I agree. The laws of physics are the same in all inertial non-accelerating reference frames. It wouldn't change. Is that the correct way to say you're playing ping pong? Is ping-ponging? Yeah, it wouldn't change if you had binoculars or not, no. Okay, do we need another one? A boy. He's on a plane to Disneyland. Yay. He drops his ball down the aisle. The ball rolls 2 meters in 1 second. Do we know how to calculate the speed there?
Yeah.
I hope so. 2 meters, hey, that's 2 meters a second. If the plane has a speed of 800 kilometers an hour, what velocity does the ball roll with respect to the boy? And there's a couple of different answers you could argue that are correct. Well, there's a few things on here we're assuming, isn't it? Planes typically fly forwards. Where are the washrooms? At the rear. This plane has them at the rear. They could be, yes. I don't think the pilot goes all the way to the back of the plane. But so he's running down the aisle and he drops his ball. According to the boy, think about it. He just drops his ball. According to the boy, what's the speed of the ball?
2 meters.
You're assuming the boy stopped. He's like, and that's correct because it doesn't really say. But probably, where'd my ball go? What if he didn't stop? Then according to the boy, the speed of the ball is 0. Because he's still running down the aisle at the same speed, isn't he? Either answer is kind of correct. I just why not, Jeff? Why not? Okay, is it too much to ask you to think? Or You're seated behind the bathroom in the plane?
Yeah.
Okay, all right. Well, again, we're assuming things, but if you argue that, I can't say you're wrong, right? All right. Okay. With respect to the plane, what velocity does the ball do? That's exactly what it means, right? When it says it rolls 2 meters, well, compared to what? Compared to the floor of the plane. No. That's not. That's what it means when I say 2 meters in 1 second. It means according to the floor of the plane. Someone on the ground looks up into this plane that has a glass floor and notices the ball rolling. So this thing, like I said, planes typically go forwards. He's running towards the back at what speed? Or the ball, not him. I don't care about him. According to someone on the ground, yeah. Okay, and if you draw a little picture, hey, piece of cake, right? Take the difference. Is that, no, it's kilometers an hour, not meters a second. Oh, you know what? Yeah, let's not even, okay, let's assume that's kilometers an hour. I don't think I did that before. It's not, this is kilometers an hour, that's meters a second. Let's assume it's the same units, okay? I'm not here to try to do kinematic stuff. Okay, so just take the difference, right? Lastly, a stewardess. Have you ever seen a male stewardess? Do they call them stewards or stewardesses or stewarders? Stewards? Oh, there we go. Then we don't have to worry about the sex, right? What do you call a male nurse? A nurse. Yes. Okay. She's walking towards the cockpit. Now, Reese, do we have cockpits in the back or are we good here? All right. So she goes to the front at 1. The ball's rolling where? The back at 2. So according to her, the ball rolls that way at 2. She's going this way at 1. If she turned around, according to her, that ball's going 3. Yeah, right? Now, one thing to add. We've done vectors. This is not these vectors added, is it? It's not the vector sum. I'm not going 2 that way and 1 the opposite way, meaning 2 minus 1, right? Do I need to say that, or is that just common sense? If these are vectors and you add them, you know that's the sum of those 2 vectors, right? So it's not vectors. If you're, okay? So 3. All right, that's it. This will do, nope, not today. It's on your worksheet, but just wait. Okay, don't answer that yet on your worksheet. So do worksheet, and those ones in the book, I talked about them, but you can do those too. Which is what? Page 261, 1 to 5.